I hope. Then I will handle it. I don't know what I did with all of my space. Okay, here it is. Okay, so what did I say? If I have a what's going on? Now this one crashed. Should I say okay? Okay, now. Okay, it works now. Okay, what did I say? I said that I can represent a line and I can represent a point in homogeneous coordinates like that. And I know that these kind of line, these kind of points, x, y, 0, I am going to assume that they represent points at infinity. Okay, well, it's not an assumption, it is just by definition it comes that way. How do I know that? How do I know that? I will give you some formulas, and that will be basically it. Let's look at this one first. We say that in homogeneous coordinates, if we have two lines, if I do this, okay, if I do this, that is line number 1 and line number 2, or L and L prime, if I take the cross product of these two lines, I will get the intersection of these two lines. Okay, that's one theorem, and that's one theorem, and the proof is trivial actually. One question for you: if I have two vectors, okay, x is a three-dimensional vector and dot product y is a three-dimensional vector, okay, if I do the dot product of these two, what kind of thing I get out of these two, this dot product? I would get a scalar, right? I would get a scalar. So how do you do that? x1, y1, and z1 dot, not good. I am going to make this like that. Okay, so x1, x2, and x3, this is my vector x, and multiply it with y1, y2, and y3. If I multiply it, how do I do that? x1 times y1 plus x2 times y2 plus x3 times y3, right? So I would get a scalar out of it. That's why I know. How about this one? If I cross product two lines or two three-dimensional vectors, what would I get? A vector of size what? 3, right? Again, so if this is a three-dimensional vector, 1, 2, 3, 1, 2, 3, you would get a three-dimensional vector. Let's think about it, okay? Let's think about it. Three-dimensional vector, line vector, three-dimensional vector, line vector. I get another three-dimensional thing. What kind of thing is this? Okay? Let's talk about this. Let's say L and L prime. I get a three-dimensional out of it. I have a vector A. If the multiplication is 0, what would you say?
L or L prime is 0.
Say it again.
L or L prime is 0.
Well, I know it's not 0. A is a three-dimensional vector. Let's say A is a point. Okay? Let's say A is a three-dimensional vector, and every three-dimensional vector is a point in homogeneous coordinate system. If I multiply this A with this three-dimensional vector, what does that mean? Well, this must be a line, and this A is on that line, right? I can interpret it that way. How about this? If this is K, if this is a line, okay, if K is a line, is a three-dimensional vector, and this is a three-dimensional vector. So this must be a point that lies on this line, right? Okay, I can interpret it that way too. How about this? Can I write this? L cross product L prime times L 0. Can I write this?
Yes.
Of course I can. Why? Because L cross product L prime produces another vector that is perpendicular to both of them, right? So I am producing something perpendicular, okay? I am producing something perpendicular to both of these lines, and if I multiply this three-dimensional thing with L, that means that I am multiplying two things that are perpendicular with a dot product, and the definition of the dot product says that you should produce a zero, because if two things are perpendicular, okay, then if this is I and this is J, the dot product should produce a zero, okay? I know this one. Well, then in that case, what kind of thing is this so that it produces zero? So this must be a point on both L and L prime. I can do the same thing with L prime too, okay? So this thing must be on both L and L prime, right? So that means that it is the intersection of this L and L prime. Okay? So if you cross product two lines, then you would get the intersection of those two lines. Similarly, if I do the opposite way, if you cross product 2 points, then you will get the line that goes through those 2 points. Very elegant, very nice properties and easy to prove. Okay? So line joining 2 points is just cross product them. Intersection of two lines, just cross product them. That's it. Okay? So this comes from the definition of the homogeneous coordinates. Okay? Points from lines and vice versa. Good. So to get the cross product, you know what it is. Okay? You know what it is. Can we do this? Let's write the formula for this line. Y is equal to 1 in homogeneous coordinates. How do I write it? How do I write this y equal to 1 in homogeneous coordinates? Okay, let me do that. Ax plus by plus c is equal to 0. I know that y is always 1, right? B times 1 ax plus c 0. What kind of a and c should I choose that it always makes 0? X can be anything, so I'm going to do this. Let's pick a as 0, 0x plus b plus c 0, right? So I'm going to choose b as minus c, right? B is equal to minus 0. And let's do this. X is, okay, A is 0, B is 1, and C is minus 1. Would this work? 0, 1, minus 1. Okay, multiply this with, let's look at this one. This one. What is this point? Tell me that point. That point is x is 0, 1, and 1. Let's multiply it. It gets 0, right?
Yes.
That's correct. How about this one? 1, 1. Let's do it with 1, 1. Okay. Let's say 1. Again 0. So anything on this line, okay, let's put 10 in here. So it's going to work. So 0, 1, minus 1 is this line. I found it. This is 0, 1, minus 1. I found it. How about this one? Similarly, if I do the same thing, it's going to be 1, 0, minus 1, right? This is x is equal to 0. X is equal to 1. Okay? So I have two lines. x 0 minus 1, sorry, 1 0 minus 1 and 0 1 minus 1. I get the formula. Let's do the cross product. See what kind of intersection we are getting. Let's do the cross product of it. How do we do the cross product of these two lines? Okay, this is the formula, right? This is the formula for the cross product. I, J, K, and 1, 0, minus 1, 0, 1, minus 1. Cross product of it. What do we get? This times this. No, this times this. Tell me what it is. 0 times minus 1 minus minus 1. So it is plus 1, right? Is it correct? Plus 1 I minus okay, minus plus 1 J plus this one 1 K. So it is 1 minus 1 and 1. Is that correct? Did I do it correct? Not correct? This is minus 1 minus. No. It is minus 1. This is minus 1 minus 0. Yeah, I think it is correct. This one is minus 1. Oh, okay, minus 1 minus 1. It is 1. It is 1 1 1. Sorry, because there is this is minus 1, right? Minus 0 plus, there is a minus in there, so it is a plus 1. So it is 1 1 1. It says that if you cross product these two lines, you are going to get 1 1 1 as a point, intersection point. Okay, what is 1 1 1 in R2? It is 1 over 2 1 over 2, right? 1 comma 1, which is this point. So it worked, right? It worked. So far you are looking at me like I need this when I was 12 years old. So what are we doing here? But you didn't know this when you were 12-year-old. Let's do this. Okay. What is the formula for this one again? Okay. It is 1 0 minus 1, right? 1 0 minus 1. How about this one? It is what? It is 2 0 minus 1. 2 0 minus 1. Is that correct? Let's do that. Let's put this on this one. Okay. 2 times 2 y times and minus, yeah, 2 0 minus 1. That's correct, right? So let's do the intersection of these two lines. Okay, let's do the intersection of these two lines. How are we going to do that? I, J, K, 1 0 minus 1, 2 0 minus 1. Okay, it is minus 1 minus 2. It is minus 3. Is that correct? Say something. Minus 3, is that correct? Minus 3i minus, oh no, I did it wrong, sorry. I was doing just the other way, okay. So 0 times minus 1, 0 times minus 1, it is 0. Is that correct? Yeah. And then minus, now it is minus 3, right? So it is plus 3. And then the last one is 0. Okay. So the coordinate of the intersection of this one is 0 3 0. Okay. 0 3 0. Can I Can I bring it back to R2? No, because there is a division of 0. So this point must be in the infinity, on the infinity. I cannot bring this back to the R2 non-homogeneous coordinates. But let's verify if this point is on these two lines. Let's verify it. 0 times 1 plus 0, okay? 0 times 3 and minus 2 times 0, it is 0, right? And I know that it is the same thing for this one too. I know that this point is on both of them. That means that it is really the intersection of these two lines, and it is at the infinity. Okay. Now I have a geometric model that can deal with the points at infinity. Okay. Now I can talk about the points at infinity, and I can project those points from the point of infinity to my regular image coordinates in terms of rows and columns. Okay, so this is called image homogeneous coordinates, and this is really a trick that we use all the time. Remember, when we need to do stuff like this, the square root of -1, we couldn't do anything. What kind of number is this? I cannot do that. So instead of using a single real number, why don't we use 2.1 comma I 5.2, so complex numbers. So instead of using a single number to represent a number, why don't we use two-dimensional numbers to represent numbers? So that's why they invented the complex numbers, right? So you just add one more dimension, your solution space becomes much larger. I can play any kind of tricks. Okay, I know that many of the complex numbers are real numbers. I know that too. But some of them cannot be converted back to the real numbers. And if you define the mathematics of it, the algebra of the complex numbers, and I can live very happy. I can solve the polynomials of third degree or the second degree with the help of the complex numbers. And I'm doing the same thing here. Instead of using just two-dimensional vectors, why don't I use a three-dimensional vector to represent a two-dimensional point? In that case, I will be able to represent lines at infinity and represent points at infinity. That's going to make my job a lot easier. And next week, I don't have the time anymore right now. Next week, you are going to see that it's going to be very useful in terms of projections too. I can project all those vectors, okay, very nicely to my image planes using very elegant equations of linear algebra. Okay, so homogeneous coordinates, linear algebra is going to make our jobs a lot easier to deal with the geometry of the images. I guess I used 10 more minutes of your time, sorry, but I couldn't stop there. Next week we will start from this position. That will be it for today.